Good morning, everyone. We are going to talk about command and data handling avionics today. So the hardware. This diagram might be familiar. It's a block diagram of the different components in a command and data handling system outlined in this dashed line with signals in black and the data buses in blue and green. You'll see in here that the components listed are clocks, watchdog timers, processors, memory, mass storage, data bus, input-output interfaces, and then we'll conclude with integrated computers. So we'll talk about each of these components that you'll see included in a command and data handling system. And if we were to manifest that block diagram into an actual physical system, here is a representation of the CDH system that HSFL is using for the high time mission. So here you'll see that the command and data handling system is a conglomeration of different boards. It's a stack of boards, which includes some compute module, which has the processor. We'll talk about different types of processors. There are different ports like Ethernet, I2C, RS422, USB. There's some memory system like the SD card. We've got other components like CAN is a data bus. And then we've got custom interfaces with, say, a camera link, an X-band radio interface. So this just gives you an idea of how these components can be manifested into integrated boards. Okay, so let's get started on describing what clocks are. So in the textbook, there are two different types of clocks that I discuss. There's the crystal oscillator and there's the atomic clock. On this slide, we're just looking at crystal oscillators where a crystal oscillator offers time by oscillating a crystal. So you'll see here on the far right, there are different modes for crystal oscillation. Essentially, you're taking this very well-known material, typically quartz, and you are taking advantage, you're leveraging the fact that you know the frequency at which it resonates at, and then you measure the amount of oscillations, and that will give you some known time. It typically looks like this as a component. You typically mount it to a board. You'll also see it represented in electrical schematic diagrams like so, where here is the actual symbol for a clock. Okay, so there are some questions here. Crystal technology is no longer new. Has a reputable database been constructed that can provide engineers the top choices for their given parameters? So yeah, it's definitely the case that crystals are not new. And we should certainly know for different materials, for different manufacturing processes, what the most stable or precise clocks are. So yes, I think maybe some database is out there. I would assume so because they've been around for so long. But regardless of whether a database exists or not, your electronics, your data sheet should tell you the parameters or characteristics of your clock on board. Next question. Is there a certain age at which these crystals become out of date or age to the point where their frequency has shifted too much? So there's this question of, when do we descope these crystals from being clocks? And there's a second part of the question about aging. So it's certainly true that these resonators or oscillators can age. The crystal itself, there was discussion about material outgassing and how the material itself can change, but also structurally, maybe the components within the chip itself fatigue and experience hysteresis, which is some change the material that changes its mechanical properties in a way of like creep. So yeah, those processes can age a crystal so that their frequency shifts. And it's a matter of, can you handle this inaccuracy in timekeeping? And so my answer to that is, if you are just relying on your clock, then you may run into some problems. But if you update your clock with some kind of external reference, like the ground station is sending a command, and within that command, there's a reset of the clock by updating what your ground station is reading, then maybe you can handle this frequency shift a little bit more. And then down here, what types of composition changes have been recorded for these types of crystals? So I talked about material outgassing, and I talked about hysteresis, which offers some slow creep of material change. So those are kind of composition changes that can occur for crystals. Atomic clocks, on the other hand, instead of relying on some physical motion of a crystal, atomic clocks keep track of the radioactive decay of some materials. Specifically, cesium is a very popular material for atomic clocks. So here you'll see a cesium core, and I think this is the outside that encapsulates the cesium core. This is one of, well, it's a picture in black and white, so you can infer that's old. But here is an atomic clock. The heart before it's put in the oven that will vaporize it into a beam of atoms. On the bottom left, you'll see why you need a kind of cesium oven. This is how an atomic clock works. So you have the cesium oven, and it emits a cesium atom beam. This atom beam is then directed into some oscillator that then can keep track of frequency that converts it to time. On the far right, you'll see a chip version of an atomic clock. So technology has progressed enough that you don't need to have this oven, you don't need to have this large tube or distance for the atom beam to travel. Instead, you can condense everything, you can collapse the whole setup into this chip. This has been a relatively new technology development, so that's pretty exciting. Previously, the atomic clocks have been rather large, but this smaller miniaturized version of an atomic clock can enable small satellites to be much more capable. So we have some questions here. Is there ever a point in time where the correction is too large, where there's no point in correcting the satellite clock? I think that if you have the ability to correct a clock, you should absolutely do so. Just because the clock is going to drift doesn't mean that you should abandon it altogether, because there are points where your satellite is going to rely on the local clock and you don't have communication with ground. So what do you do then? Ideally, you want to reference a clock that is as accurate as possible, even if it's drifting. On the bottom left, is there a theoretically more precise way to measure time, or is the quantum clock at some sort of precision limit? So I think the atomic clock is certainly very precise. The reason being is that it has a very, very, very high frequency. So you could get more precise if you use a type of atom, a material that oscillates at an even higher frequency. that is just as well characterized and something that we can measure. So I'm not sure if the cesium atomic clock is the most accurate. You know, there could be atoms out there that are oscillating more frequently. But I'm going to say by intuition that this kind of radiation is one of the highest frequencies that we can measure. Yeah, this is probably one of the highest frequencies that we can physically measure. So I think it is approaching some sort of precision limit. Okay, so now we're moving on to the next component called a Watchdog Timer. So Watchdog Timer is connected to a clock, like we just talked about, and it's also connected to a computer. Its job is to be a watchdog, in that it is constantly reading a computer's output, and it's also reading a clock to ensure that the computer is still healthy. The computer is tasked to always send some kind of ping of whether it's still healthy. So if the watchdog timer does not receive some kind of healthy signal from a computer, in this case, it could be that the computer was zapped with radiation and its logic is all messed up. In that case, the watchdog timer would send a timeout signal and reset the computer. So here is a video of someone demonstrating this with a very simple circuit and board.
So I'm going to activate the...
Oh my gosh, okay, one sec. Okay, so let's watch the video.
Program, the LED will come on, and then I'll have to hit any key on the keyboard to keep the program from timing out with the watchdog timer. So as long as I'm hitting any key on the keyboard, I'm sending the CWD command to reset the watchdog timer within that 2-second time interval. So if I stop hitting the keys for 2 seconds, it's going to time out. The watchdog timer will time out my program and reset the microcontroller. So I'm going to stop pressing the keys on the keyboard, and after 2 seconds, you can see it timed out and reset the microcontroller.
Cool. Okay. Yeah, so that's you know, a very simple function, but is very important for spacecraft where, you know, it's under this space environment that has radiation that could potentially mess up the computer, and your spacecraft, you know, is operating under critical conditions. So this is one of the ways where, since we're far away and we can't manually press a restart, the watchdog timer does that for us. All right, let's move on to the world of processors. So you've probably seen these terms when you're buying computers or speccing out what kind of characteristics you want for your laptop. Every computer, whether it's on ground or whether it's an embedded computer in space, is going to have some kind of processing unit. The most common one that I've seen is the central processing unit, or CPU. You can characterize a CPU by its instructions per second, its flops, its performance per watt, its low power energy state, and its real-time operating system. On the bottom left, you'll see what a CPU looks like if you take its casing off. It's this conglomeration of a ton of very, very tiny transistors that offer logic. On the right, you'll see an integrated processor. Here is a microprocessor that's used on the BeagleBone Blackboard. So in a system diagram form, you can see on the upper left, we have some ARM Cortex processor. And you'll see some of those characteristics like clock speed up to 1 gigahertz up here. And then here it is, here's the processor in the context of all the different components. Another type of processor is a graphics processing unit, GPU. It has been getting a lot, GPUs have been getting a lot of attention with machine learning on the rise, specifically for processing image data. So right now we're in this growth of computer vision, which is the ability to take images and, classify images to different categories of objects or to detect objects. So you notice that GPUs are used in a lot of those applications. GPUs differ from CPUs in that they are very power efficient. They're computational workhorses for image data versus CPUs you use just more generally for like number crunching, for sequential operations. GPUs have a smaller quantity of cores, can process a smaller quantity of instructions, but they have higher parallelization than CPUs. So that's why they're so good at processing images. On the high-tide mission, a GPU is used on board because we are taking a lot of imagery and we're processing a huge amount of scientific imagery. So it makes sense to have a GPU on there dedicated to do that kind of work. Okay, another type of processor is called an FPGA. FPGAs are like muscle memory if we were to talk about the different processors and relate them to the body. So FPGAs have actually programmable physical connections that are embedded in the chip. The CPUs and the GPUs are these transistors where you're sending these transient electrical signals, and after the electrical signal passes, there really is no memory retention. Whereas FPGAs are encoded such that their circuits are physically in that shape to allow signals to go through and process consistently. So for that reason, FPGAs can be more resilient in radiation-heavy environments. Here is what an FPGA chip can look like. Here's an array of them. And then if you were to look at a schematic of FPGAs, you'll see like physical connections, programmable interconnects, and you'll see within a little block, you can have these set logic blocks. These have been really popular lately because the process to program these little units has been easier. An obstacle prior to adoption is that programming these FPGAs had to be at the manufacturer, but now the programming unit that wraps around an FPGA comes with the chips now, so you can iterate on site when you're developing an FPGA. So they have been rising in popularity. Okay, now let's get into memory. So there are different types of memory. There is read-only memory. This kind of memory stores information for immediate use in a computer. Let's see. This kind of memory, even when it's powered off, still retains the information, and it's called non-volatile memory. Read-only memory is, as the name suggests, read-only. This type of non-volatile memory is defined by the manufacturer and cannot be changed. This is typically advantageous for storing software that does not change throughout the system lifetime, usually dedicated to firmware. Although read-only memory can be reprogrammed with special instructions and some specific voltage setting, read-only memory can only be rewritten a limited number of times. If you recall, when CD-ROMs were a thing, you could, I think the older ones, you could write once and then distribute. But I think the more modern ones, the technology came out that you could rewrite these CDs. Another type of read-only memory is USB. Typically, we'll see read-only memory as chips for our embedded computers. And if we're looking into the past, here is what read-only memory looked like for the Apollo mission. It was in the form of these ropes that were hand-woven by a lot of female technicians, actually. You can see some cool pictures of that. Okay. So another type of memory is called random access memory. Random access memory is computer memory that can be read and changed, typically used to store working data and machine code. RAM is volatile memory, which means that if power is to shut off from the system, from the RAM chip, that it's going to lose all the information that was on it. So there are two types of RAM. There's static RAM and dynamic RAM. Static RAM is typically used for control processing, like buffering between cache and storage as the processor's main memory. And then, let's see. Dynamic RAM is typically used for data processing applications, much like static RAM, but for data. Dynamic RAM is extremely common in personal computers, like flash memory. So here you'll see a comparison of static RAM and dynamic RAM. So static RAM, it's faster, typically smaller, more expensive. And here's where I really want to drive the point home, where they're used. So static RAM is used mostly in cache memory, whereas dynamic RAM is used for main memory. So this is like processing, and this is more like data. And yeah, they both have their functions. So if you look back to the computer that I showed, the integrated computer, you'll see that there is the presence of both SRAM and DRAM. Okay, and then the last part of memory that I want to go over is flash memory, or non-volatile random access memory. So that's a little confusing, right? Because we were talking about read-only memory being non-volatile, and we were talking about random access memory as being volatile. But yet, this is a mixture of both. It's non-volatile, and yet it's random access memory. So the best known form of NVRAM is flash memory. Flash memory is a type of non-volatile memory based upon electrically programmed read-only memory technology. Flash is between read-only memory and RAM mid-speed memory, which can be easily read and written. Flash memory is typically used to store large amounts of data for startup, like device configuration, calibration tables, boot code, and debug configuration. Flash usually stores software or firmware that is expected to be updated, but otherwise does not change during normal operations. So it's this hybrid of, even when power is off, this kind of memory retains the information, but it has that added advantage that you can update and change this memory. It's not just read-only memory. It has capabilities beyond that. So here you'll see a physical manifestation of a flash memory chip. And then on the right, I have some diagram that shows flash memory here, but then the radiation effects in flash memory. It can be that radiation changes the charge of some gate, which affects the memory inside. So this cell in a 0 state can flip to be in a 1 state, which changes and garbles the information that's stored in a flash memory. Okay, so now we're going to talk about mass storage, which differs from memory. So when we were talking about memory, we're talking about these like temporary closets of information, whereas mass storage is where we're going to be like dumping a ton of information and data. It's more permanent in nature. It's where a lot of data sits and doesn't have to flow too heavily in between. So we've got hard disk drives, and we've got solid state drives. You'll see a lot of acronyms that the hard disk drive is acronyms to HDD, and solid state drives are acronymized to SSDs. Here on the left, you'll see an anatomy of a hard disk drive where there's this rotating magnetic disk, and that disk contains a ton of information on the order of, say, 1 terabyte, depending on your laptop or your desktop. And then we've got solid state drives, which come in the form of like SD cards. So they differ in that you see there's this rotating disk on hard disk drives. That's some mechanical mechanism, whereas solid state drives do not use mechanical parts, but they only use electronic circuits to read and write digital information. Solid state storage is a type of non-volatile memory that typically utilizes electrically programmable non-volatile flash memory. So these have been increasingly popular, not only in personal computers, but also in space. Okay. So now we'll talk about input and output interfaces. These are not the distinct components or nodes, but they are the interfaces. They are the connectors between distinct components. So here you'll see a block diagram where we've got the avionics, and it has to connect to all of these different subsystems. There's got to be a lot of data transfer that is sometimes one way, sometimes two way. So how do we connect these different components together to transfer information? What are their different characteristics that enable either very fast data transfer or very resilient radiation resistant transfer? So we'll look into those. So the data bus is the main pipeline for this data to transfer between. On these boards, these PCI 104 single board computers, the data bus is this large header of pins. There is some kind of regulation embedded in the board beneath, but the reason why we have this large stack is because if you have two, you can directly put a header from one board onto a header of the second board. In the stack formation, all of the information is going to be routed to this data bus on top, these header pins, and it can be directly transferable in this really short distance connection to the second board on the bottom. There are other data buses that exist. For example, this engineer is looking at a CAN bus where this large board, somewhere on there, is also the same pipeline, but in a different physical form. The data bus is in charge of quick in-succession data routing and prioritization. They are reserved for high-speed data transfers, typically connecting the processor to the peripheral subsystems. In the textbook, there are other data buses that are mentioned, like the MIL standard, but for now, I'm just going to move on. Okay, so now we can talk about port connections. These are the more isolated connections. So the data bus was very integrated. It had the centralization of connections. Whereas these port connections are the actual individual connections that go between specific components. So in the textbook, there are just a list of different connections like GPIO, general purpose input-output, which you can see here on this board. The pins can be broken out to be a bunch of different types of signals that you can connect to and typically are listed in data sheets. You'll also see connections like UART, Universal, what does it stand for? Universal Asynchronous Receiver Transmitter, which physically look like this and have a lot of applications like through GPS receivers, Bluetooth modules, wireless communication systems, RFID. You'll also see connectors like I2C. Yeah, I2C is synchronous, and you'll see this in barometric pressure sensors, gyroscope and accelerometer modules. And you can see in that physical board that the pin signals are labeled so that when you're connecting a cable, you're connecting the correct pins and transferring the right pins to the other side of the cable that's communicating and breaking out those same signals. Okay, so this is what it looks like when you're looking at the hardware. Now, this is what it looks like for electrical schematic diagrams and for message packets. So UARTs, remember we have one node that we want to connect to another node. If we were to create a cable between them, there's some transmitting signal that you want to connect to the receiving signal on the other side and vice versa. UART message packets look like so, where you've got some kind of like a prefix bit, a start bit, you've got your data frame, and then you have stop bits. I2C, here is what serial connection could look like, where you have serial data pins that go directly from, there's this connection configuration where I2C allows one controller, so a master, to connect to a bunch of downstream components, which are commonly referred to as slave 1, slave 2, ... slave n amount of components. The idea is that one master can control a bunch of other components. Yeah, so what I wanted to show from this slide is that the physical manifestation looks like a bunch of pins, but the actual digital connection can vary in the types of signals and the way that you connect. The message packets that are going through these different I/O interfaces can also vary. Okay, we also have other choices like PCI Express through an RS-232 port. We have something more modern called SpaceWire. You'll notice these USBs and Ethernet are also used in spacecraft. And their port connections look like so. I'm running short on time, so I'm just gonna skip it. Okay, so we did talk about a bunch of different components, but unless you're designing a custom computer, it's very unlikely that you're going to hand pick every component. Instead, it's very likely that you're going to work with an integrated computer that has all the components already set out for you. And it's just a matter of checking that each of these components are sufficient for your application. They can come in the form of, here is a integrated computer block diagram where there are a lot of the components broken out. Integrated computers can also come in the form of microcontrollers, where this chip, this microcontroller, has a bunch of the circuits, a lot of the components in circuit form embedded into this microcontroller chip. So that's also an option. They're getting increasingly common and popular. And then here is the Artemis CubeSat onboard computer, where we have all of these components laid out. You'll see that there's an Ethernet connection, a USB connection, micro HDMI. Our memory is a micro SD. We've got DDR3 RAM. We've got this expansion header with a bunch of these I/O interface that you can use. So yeah, this is what we're choosing to use. And I answered all the questions. All right, so now we're gonna transition to team activities.